We go for circuits which can give us programmable dead times. We need to introduce a deadband time, but this deadband time should be programmable. I should be able to control it without any change in the hardware structure. And that is exactly what you see here as a deadband unit. So your digital controller should have a provision to generate deadbands like this. That also is there in these C2000 controllers. And once again, coming back to our AICTE Embed, you see how easy it is to control our deadband. See this particular thing, deadband. You have the configuration. As of now, it is disabled. If you want, enable it. While you enable it, also there are plenty of options available. All available at just a click, a mouse click. We don't have to compute the register values, we don't have to find the address of that particular register, we don't have to write a statement which assigns this value to the register, nothing is required. You just do something, maybe one program I will just show you, so that you can once again appreciate the use of these kinds of model-based tools. A simple programmable process using our PWM unit. So I have some program which generates a PWM signal. Transition is configured, the symmetry is configured, the time period, that is frequency of the PWM pulse is configured, everything is done. I'm good to go. You now see how long it took us, hardly a minute. You just see the equivalent C code for this. Now the logic which we have created is only PWM logic, PWM generation logic. But in addition to that, see what and all is there. There are some chip features, general chip features which you have to configure. Starting from PIE all the way to watchdog timers. All those things are by default configured there. And including your, where is it? Yeah, see this? Time and period, compare register, action qualifier, everything is populated there. So naturally it is cut down, it is going to cut down your development time. That is the point which I was trying to make. Now let us come back to our presentation. From now on I will try to run through the remaining slides quickly. Naturally when there is a fault, you will be willing to shut down the converter. So your embedded controller should have a feature to shut down the controller also. So that is available in the form of a trip mechanism in your C2000 microcontroller. Trip mechanism. Obviously you say the relay has tripped, which means that a fault has occurred and the relay has isolated the load from the supply. Same mechanism, similar mechanism, we can get it from here. Now these trip modules have different functionalities. It can, whenever it senses a fault, immediately it isolates the one part of the circuit from the other. The PWM logic isolates the load from the source. You have a converter in between. That converter switching signal is made as high impedance state, which means that it is as good as the converter getting shut down. Converter is shut down, so obviously load source is isolated, trip mechanism. So that feature is required, that is also here. Now these are related to control aspects. We covered only PWM because that was the important topic related to any kind of converter control. Other things we didn't touch it. We will come to the sensing part. So you will have a requirement when it comes to motor control, a requirement to sense the load current, load voltage, next speed, direction of the motor. Physical quantity, electrical quantities, current, voltage. So obviously you need a device to sense these voltage and currents. Motor control, I am not taking other environmental parameters, only voltage and current. So you condition the signal appropriately, then what you will do, you will give it to the processor. Now this is analog signal on this side, the current which is flowing through the load or your motor in this particular case. The voltage across the motor terminals, analog signal. That analog signal need to be given to a digital controller, digital processor, which means that you have to make a conversion. That conversion happens through your ADC. Now before you start using these ADCs, the signals have to be conditioned, all those things. If time is required, we will discuss it. So once, assuming that you have given the manipulated or modulated signals or Once you have, usually it will be 230 or 1 ampere signal or 10 ampere signal, isn't it? Those things you have to make it compatible with the ADC terminal. It accepts analog signal in the range of 0 to 3.3, all CMOS based controllers. ADC accepts only signals in this range, 0 to 3.3. So assuming that you have made all the conversion and given to it, what else we need to do it? That's what we are going to see here. Now it is not just one single quantity which usually you will be sensing. Take the case of a 3-phase inverter. You have the requirement to sense at least 2 of the phase currents and 2 of the phase voltages. If you go for unbalanced conditions, 3 currents, 3 voltages. So obviously you have a requirement of more than 1 ADC channel. So usually manufacturers will provide a setup where you have different channels available. This is a very old microcontroller's block diagram, 2407, it is obsolete device. It is simple to understand, so I have used this. If you see the present Piccolo Delfino devices architecture, it is much more complex. It is a little bit easy, so we will use the same diagram. So you have 16 channels in this particular case. 16 channels, 0 to 50. One of these channels will be connected to the ADC at any given time based upon the configuration you are making. Once again, to make this configuration, you have to assess what should be the detail which should go in the control register. Then you have to do that, assuming that you have done all those things and assuming that the conversion has taken place. That result will be available here in the form of either 12-bit results or 10-bit results, depending upon what ADC you are using. In a fraction of a second, this conversion will be done. And those results will be stored. The digital data, converted digital data equivalent to the analog data will be stored in these result registers. It looks as simple now, but when it comes to control, it is not as simple like this. Because you have to tell the ADC when you have to start the conversion. Then you have to wait for a predefined amount of time for the conversion to be over, sampling plus conversion time. Once this is done, you need to give some amount of time to the result to be stored in the result register. Assuming that all of these things are done, you will be taking that value and you will be processing it. So all these things, once again, are to be done if you want to sense any physical quantity. Just a small thing. Just like your PW module, here also you have set up procedures to be followed, starting from resetting the ADC all the way to triggering the SOC signal in order to start the conversion process. So once again, all of these things should be done or can be done only after configuring these peripherals properly. So you have something called as control register, you have something called as maximum conversion register, channel select registers, all of these things should be configured. Now if you look here, the process of configuration once again have been made simple in these kinds of model based tools. You put all these things in place, you click it, then you generate the C code, auto generated C code, dump it to your device, put it in the design and start testing it. Now you have something called as eCapture modules. So these eCapture modules functionality is what you will be using to sense the speed or perhaps to determine the direction of rotations. First thing we saw is control. Converter, motor control setup is there. Your converter need to be controlled, provided with switching pulses. How that will be done? Using PWM signals. And this particular PWM generation is based on environmental parameters. So to sense the environmental parameters, we saw how to utilize the ADC. The other environmental parameter, that is your speed, can be sensed by using these capture modules. So this one, yes, just look into this. Assume you have some sort of rotary encoder which generates a trail of pulses like this. By counting the number of pulses over a period of time, you will be able to determine the speed. Now speed, the unit, just recollect it, it is rotations per second, rotations per minute, whatever it is. There is a time frame involved there. So for every rotation, there will be n number of pulses. So if we simply calculate the n number of pulses, we will be able to determine the speed. Now to do that using a digital controller, what needs to be done? You look into these pulses, you count the number of done produced over a period of time, which means that you need a counter which detects these edges and keeps counting. Fortunately, we have functional hardware circuits to do that. Those things are called as capture modules. It captures the edges and it increments the counters. Now, an enhanced version of this capture module is what you have here called as quadrature encoder pulse signals. Once again, these are used for detecting the speed of your motor, velocity of your motor. In addition, you can also determine the direction and angular position. How you will be, look into this particular animation that you have there. So this is a quadrature encoder pulse, what you see there on the other side. Quadrature encoder, which means that there is a phase difference of 90 degrees between these two pulses. The way these pulses occur, whether A pulses rising edge occurs first or B pulses rising edge occurs first, will give us intimation about whether the motor is running in the clockwise direction or anti-clockwise direction. Now, direction problem is solved, finding out the direction. Why direction is required? Your FOC algorithm, if you have gone through it, you will see based upon the direction you will be determining certain coefficients and then you will be controlling your inverter. So obviously direction is an important thing. If you look into certain motor control applications like your PMSM or BLDC or perhaps your simple servo motor, you will be requiring the position information also. So those position informations can be obtained by looking into these pulses. The pulses generated because of these slots present on the encoder wheel, comparing it with this index slot. There will be only one index slot and you will be having n number of encoder slots, which means that only one pulse will be produced. If you count the index pulse, only one pulse will be produced for every rotation. So keep this as a reference. For this signal, you will be able to determine the velocity, angular position. With reference to this, you count these edges. That will give you the exact position of the rotor, 360 degree, whether it is at 90 degrees or 135 degrees, you can exactly know it. To determine all these things, once again, we have a projection in our C2000 microcontroller in the form of QEEP modules. You just take an encoder, feed the encoder pulses to the QEEP module. The QEEP module will do the rest of the job. See how things are getting simplified. Imagine you doing the same thing all by yourself. You receive the QEEP pulses just to sense the direction. You count the number of pulses through your program, of course. You write an instruction to count the number of pulses. Then you manipulate that information. Total count divided by 60 time seconds or minutes. You count it. Then you produce a result. That result you feed it to the control algorithm. See how complex it is? So these kinds of peripherals are there for making our system design tasks easier. Only thing, we have to identify them and start using it appropriately. So we have covered different kinds of peripherals which will help us to sense voltage, current, speed and to control our converter, that is your EPWM module. And the same thing is what we might see in our hands-on session also if we have proper time. Just to give you an idea about how the interface will look like. You see this? This is a kind of HIL module which I was talking about. Hardware in-loop simulation module, what you see here. The actual hardware is here. The actual hardware is here. Some of the control information is going from the screen. Some of the control information, not all of them. Feedback plus the output, all those things are obtained from the hardware. The program is running on the target device. It is not very clearly visible here. You see a red color thing there, that is actually a development board. The program is getting executed from there. So you just monitor, and this is a final phase of development. You had model MIL, model in loop simulation, then you had software in loop simulation, model in loop simulation, software in loop simulation, processor in loop simulation, and hardware in loop simulation. HIL comes at the last stage of development. That HIL implementation is what you see here. Once again, these kinds of promotions we don't see in non-model based design tools. So things related to Altair tools and their usage, Chandrakumar sir will tell you in detail what are the different tools which are available and how you can exploit these things to accelerate your design and implementation process. Just quickly let me run through certain things. While you are using your ADC, certain things you can anticipate. For instance, when you take the physical signal which is processed, and when you give it to the ADC pins, one thing for sure you can anticipate, the impedance mismatch will be there. Your input pin has internal circuitry like this. You see this? Internal circuitry. Naturally, when you bring some signal from some other circuit, the Thevenin equivalent, all those things recollected, when that particular the moment it makes contact with the pin, immediately this side the impedance will get altered. Because of that, you will lose that relation between the input quantity and the output quantity. That is one major thing you will be coming across. How to rectify this issue? You have to go for a circuit which offers high impedance to this ADC pin. So this side you should have a very high impedance. Best thing, if at all you don't have any ready-made circuits available, processing circuits available, is to use instrumentation amplifiers, which will improve the impedance. It will create a high impedance path. So this ADC pin won't be loaded. So whatever response you are getting from the ADC, the conversion data, it will match exactly with the physical quantity. That is major issue. Other things are minor issues. The time duration for which you have to keep the signal steady until your ADC finish measuring these signals or sample these signals. That is another important thing we have to look into. And then usually there will be noises in these measurement signals. So that you have to remove it. So either you can do it by using passive circuits or by programmatically also we can do it. And always there will be a non-linear relation, unless and otherwise you are using any signal processing boards. Always there will be a non-linear relation between the input quantity and the output quantity. For instance, if you are measuring a temperature, that is getting converted to electrical quantity using a temperature transducer. The relation between these two won't be as smooth like a y equal to mx plus c curve. It will be non-linear. You have to account for these non-linearities before you program and control your system properly. And the last one is your instantaneous variations. So even speed, whatever you do it, your mechanical inertia, that mechanical inertia constant in a motor, it will be pretty high. Which means that this motor will be pretty much running at a constant speed. But when you see at the digital readings, even that 1 or 2 variation will be there. It will be showing, one moment it will be showing 1231 RPM. Next it will be showing 1229 RPM. There will be a slight variation there. If you feed the signal directly to your PI block, that feedback path, if you feed it directly there, obviously you will have issue, stability issue. So best thing to do is to average this over a period of time. Maybe for 100 milliseconds or 500 milliseconds, average is this particular speed value. Then feed it to your control loop, you will have pretty good stability there. So that is about your ADC. Other things are known, whatever you have. Never exceed the voltage, whatever which is prescribed for the ADC pin. Use a signal conditioning circuit. Always have a fail-safe mechanism. Not necessarily these signal conditioning circuits will be sending signal compatible with your ADC pin. So best to have a protection mechanism. Best, cheapest one is to use a Zener diode of appropriate value. And I don't know whether these things will make sense to you. While generating a PWM and when you are testing these things, it is absolutely essential that you need to have proper measurement equipment. So whatever we generally use is low-cost oscilloscopes. So there you will have issues with when you are viewing the time-varying signals. So unless we have a proper measurement equipment, we shouldn't come to a conclusion that our design and our implementation is not correct. That is one point to see, that is inadequate measurement. Yeah, this also is another thing. The deadline which can be generated to its minimum extent by any given PWM module for a particular clock frequency, it is fixed. Minimum value I am talking about, not the instantaneous value. That will be fixed. If it is not meeting your requirement, there is no other go. You have to replace the controller with something else. For instance, if at all anybody is going to work with GAN-based controllers, WBC-based controllers, when you want higher frequency of operation, this is going to be a major issue. C2000, both Piccolo and Delfino might not be sufficient. You will test it and then you can decide it. Here also, while using your QEP module, you can come across noises and then you have to use signal conditioning circuits. For instance, an encoder like this, a Chinese manufactured encoder, has a minimum requirement of 5 volts to energize it. Encoder you will have internal circuits, right? So it requires minimum of 5 volts, maximum goes down to 24 volts. Now the problem is that QEP pin or e-capture pin. You have both of them in your C2000 microcontrollers. When you look at these pins, the data sheet says not a voltage not more than 3.3 should be fed to it. You have a mismatch, so obviously you have to look for signal conditioning. And when you use the signal conditioning, make sure the signals are not distorted. That's pretty much it. We have, maybe if we have time, it's already 3 o'clock. If you have any questions, maybe demo we will see in the lab session. If you have any specific questions. I know it is too much to ask from you. One small session, more number of peripherals, more number of functionalities with each peripherals. It's very hard to digest. So I can understand thoroughly that if you are in a state of kind of enigma, it's not an issue. Just be aware that these things are there. You just have to use it based upon your requirement. Start exploring it and start using it. That's it.
Thank you, Dr. Kumaran. He loaded us with so much of information. Thank you very much, sir. Now, we will be hearing from Dr. Kumaran once again in the lab. He is going to continue the lab session. Now, it is my pleasure to introduce Mr. Chandrakumar M. From ALTE. He is going to continue the session. Sir has a bachelor degree in electrical engineering, currently working in ALTE as technical account manager for math and system design. He is responsible for technical aspects of model-based design software by ALTE, for multidisciplinary system modeling, from concept design to system simulation and hardware implementation. He has more than 14 years of working experience in the field of power electronics, power system, and model-based design for embedded system applications. Sir, it's very nice to have you here, sir. I request Mr. Chandrakumar to continue the session. Thank you. So on behalf of the Department of Electrical and Electronics Engineering and the Mayor Institute of Technology, I welcome Mr.
you all. Thank you for the opportunity given today to deliver on our innovative system on quality application. It's been quite long associated with MS Mannaya. Actually, I started interacting with Krishnan sir during 2010-12 time. I used to work with power electronics with PSIM too. Even Sanjay, Lakshmi sir was there, Pramila madam was there today. And also, Kumaran sir, thanks for the opportunity given today. And I used to interact with Kumaran sir on the embed side. So before PSIM, I used to work with embed side itself. So now it's fortunate that both the tools are there as part of ALTE. So ALTE embed and PSIM. So I don't know how many people are aware about these tools. So probably I'll be talking on these aspects. Let me quickly introduce ALTE engineering. So ALTE was formed in the year 1985 from Troy, Michigan, USA. So it's a US-based MNC. Most of the mechanical engineers knows about ALTE and especially the CAE community, but we have a lot of technology acquired, especially on different technologies like data intelligence, IoT, model-based design, multi-physics, and so on. So our revenue is almost close to $500 million, and we have global presence in 27 countries. We have 74 offices throughout the globe, and our company became public. It became Nasdaq listed, and we have around 150 plus products. We are the OEMs. We develop softwares, and we also provide supports and every aspect in terms of sales and marketing. Everything is there. So India is the biggest office in APAC region, and we have 2 offices in Bangalore. And we have different branches in India as well. So that's a quick impression about our company. So our vision of our company is to transform the enterprise decision making by leveraging the simulation driven, data driven with the help of high performance computing, with the help of artificial intelligence. So the reason behind I'm showing up these technologies is that even power electronics is connected to data analytics. So that's why going forward emerging trends will be that as well. So power electronics is the key for amplification similar way. So the reason behind this technology I'm introducing you is that in case you can also get a trial license and start using these tools for your project work as well. So we are there on data analytics, a tool called Rapid Miner. Probably you can make a note of that tool. It's there's no code, low code. So it's a drag and drop options for AI ML platform. It's not enough writing a Python code. So it's a block based approach. You can use data analytics AI platform, tool called Rapid Miner. But we are there into physics simulations, modeling, visualization, IoT, and performance cloud computing. So with respect to today's context, what are the tools we have is on the electronic system design side. So one is on the model-based embedded development, another one is PSIM on the power electronics for doing analog digital circuit simulations. And so to talk about not only as an electrical side on the power electronics and embedded systems, we have various technologies. For example, we want to design a motor from scratch on the multi-physics side. So we have flux and flux motor to design a motor, transformer, generators, or any wireless charging applications. So for that we have low frequency tool for flux, and high frequency for antenna design or EMI, EMC. So we have tool called FICO, and also we have tools for code generation, that is embedded. You have already seen how you can rapidly prototype your control algorithms, talk to different peripherals like ADC, PWM, then encoder, how you can work with CAN, UART, SPI, all these peripherals, as sir has already given you their own presentation on that. So I'll be talking on that. So that's covered by embedded side. And we also have solutions on thermal side, board level, system level. PCB design tools are available, like SPICE simulation. These are all our complete offerings with respect to electronics, electrical, mechanical, mechatronics, as well as circuit and code generation. So we have tools for that. So 2 tools are already been there in MS Ramaya. One is PSIM, another one is Embed. Okay. And these are our global customers. Just to talk about, we have around 15,000 plus customers globally, and we have been there in all the verticals in automotive, aerospace, civil, defense. We are there into all this. So these are popular logos. We've been using our technologies, is what I'm saying. I'm very privileged to tell you that one of our ex-alumni of MS Ramaya, they started their own firm called Staria Mobility. So I've been quite actively working in past 3 to 4 years with a lot of EV companies. Today's talk is also on the EV, as the EV is booming up. So Staria, the guy is called Gaurav, probably you would have known him. So Gaurav is from electrical department, and he was participated in our competition called ALTE Startup Challenge. So you may be also start a own firm, or you can start coming to another, or say the competition part. The reason I'm saying is that these are all the small startups which are starting from Ather to Ola Electric. These are all companies who are especially on the EV vehicle side, they are using our tools. So I've been working with them quite actively with the Indian OEMs or global OEMs and suppliers for different applications, whether it's onboard, outboard, battery chargers, BMS application, motor control applications, converters, inverters, on all these areas of different subsystem of EV they have been working on. Okay, so this is quite good reference I'm just saying, and Gaurav is from MSRIT, and they are having a retrofit for two-wheeler. I'll be showing that model as well. So these are the product line which is part of our model-based portfolio. That is, sir has already covered on embed side. I will also introduce you what is embed. Embed is the model-based design framework, which can do software in loop, processor in loop, model in loop, and hardware loop simulation for the entire V cycle it can do, starting from simulation, design, modeling to code generation and verification. And PSIM is a recently acquired tool. Previously PSIM was through a reseller, and now last year we acquired this tool, and PSIM is part of AICTE throughout the globe, and we have a development team acquired, and everything is part of AICTE itself, and it is a dedicated, very popular tool in the market, especially in India as well as global market, on the field of power electronics, motor drives and embedded applications. And with that, we can also have Compose, which is on scripting side. How MATLAB is there. Similar like MATLAB, we have Compose on scripting, like writing code in Python, R, OML, TCL, DK. And Activate is similar like Simulink, where you can do a combination of 1D plus 3D simulations. And then Motion Solve is on the multi-body dynamics. So these are the tools just to give you an idea. Probably if you are interested, we can get the certification course. As Sir said, AICTE provides you the certifications where you can go to our university program. Students can download the free trial license for 1 year. They can start using any kind of tools and then get certified, and we can give you a placement. So we can, wherever our clients request, okay, a person with experience in PCM, person with experience in embed, and we want to place them. So if you have certain experience or certain projects you have executed, we can provide internship, we can provide you job opportunity across our OEMs. Because our solution has been used among different OEMs, so that's the reason we need manpower. So in that case, we can also help you out. That is the idea behind me talking. So I will talk about the code, but this is just a high level thing. I want to emphasize more on it. So you can get benefit out of this. So let me talk about what we as a company, we provide solution on electrification. So if we talk about electrification, there are different subsystems. So starting from you take on body structural simulation, you can talk about light weighting, and then you can talk about fatigue, durability, MVH. These are all with respect to mechanical side. But today we are breaking the silos where we work on multi-domain in terms of we need to understand the different domain aspect as well. As an electrical engineer, you cannot say that I know only power electronics or motor drives. We need to know about the entire system, how it interacts. So that with said and done, so we need to know about how different physics and different models work together. So that is on the structural side, and you also talk about thermal and fluid management. So we have solutions on fluid and thermal management. When it comes to pure or e-powertrain, we talk about power electronics. Power electronics is very key and very factor in terms of doing onboard, outboard chargers or converters, inverters, whether it's off switching, on switching, all these things you can do it. Motor design can be performed with the flux and flux motor, battery design and battery management systems, and then also the embed for the firmware deployment of the controls algorithm. Okay, so this is there, and then also virtual modeling for the vehicle integrations. So for example, for different driving cycle and different driving patterns, how you want to size your vehicle in terms of battery-driven powertrain model, in terms of looking at the state of charge of the battery, health of the battery, or sizing of your motors, what is the demand, torque demand, power, speed demand for your motors. So those aspects you want to virtually model your vehicle dynamics with the different subsystems. You can use Activate as well. So this is the entire solution what we provide with respect to electrification as a general. So let me talk about trends and challenges in power electronics. Sir is also talking about GaN, like because of using SiC and wide band device like silicon carbide as well as gallium nitride, which has its own advantage. You can use them. So that is the latest trends in field of power electronics. And then also we talk about, as I already said, power electronics key for electrification. And not only that, we see in every day-to-day life. So power electronics initially, if you look at 10-15 years back, it was used mostly on the research side and it was there, but not that much. After electrification booming in the megatrend, so it's quite popular as well there. And what is the challenge for any power electronic design in this? The challenges will be designing an optimal converter with help of keeping EMI, EMC, electromagnetic interference, and then that is another biggest challenge. And then you talk about thermal management, designing, and then you talk about performance, efficiency, size, and then power density. And you talk about satellite application, that size also plays a major role of your converters. So in that case, how effectively you need to keep your design in mind and efficiency in mind, you want to design that. So that is what the role is. So we provide you the platform, but at the end of the day, how you going to use your domain knowledge to efficiently make this kind of topology designs. That is the role the future engineers you're going to be there. If you want to work on the core side, so these are the factors which you need to keep in your mind. Okay, these are the trends and challenges in general. Not only the respective area that I'm talking about, in general these are the trends and challenges. How we going to address this is what I'm going to talk about here in PSIM. So I know most of you are used PSIM, I don't know how many of them used PSIM. So anyone, the students and other faculty members, others from other colleges. Because I saw the logo on Sir's laptop, 2022.2 version was there. The latest version is 2023 and it has quite a lot of unique features. These are complete modules. When I started my career in 2009, it was around 4 modules were there. And it was very basic, like PCM basic was there, motor drive was there, digital control, C coupler which was interfacing with MATLAB and then thermal with a minimal thing. But if you look at the current features, you will be astonished in terms of, we have a design suite, power supply design suite. Power supply can go into anything, whether it's automotive or aerospace, any industry, engineering or data centers, you can have power supply is there in terms of different type of range of power you want to work on. So power supply design is there which you can automatically design, whether it's we talk about buck, boost, flyback topologies, or anyone is aware about working on resonant converters? Anyone is working on resonant converters, half bridge, full bridge? No. The first year in tech or? That's why it will be okay. Because I'm talking about the other advanced topologies. Okay. So you can work on all these topologies, right? DC-DC, AC-DC, rectifiers, converters. Probably you will be studying that in core power running subjects. So those things can be designed using power supply design suites. EMI, EMC is another one which you can do as per CRISPR standards and MIL standards you can design. And then motor control design suite. So I'll touch upon this a live demo. And then hybrid electric vehicle, you want to have a combination of hybrid with the EV side, you can work on that. With the help of that, we have different of PCB models which goes from level 1, level 2, whether you want size or the system level simulation, sizing of LNC, or you want to do gateway circuits, or you want to do thermal analysis like switching losses, conduction losses of the semiconductor devices. Those aspects you can do it. There's also code generation for doing control implementation on hardware targets, like multi-control targets, you can implement it. So implementations, we have different targets like Typhoon XAL for XAL. In case if you want to deploy or control algorithms on Verilog or VHDL, there is another provision. One is embedded side, another one is also Verilog and VHDL you can interface with module cell. And then you can do a close simulation with MATLAB Simulink. Activate and embed is our own tool for close simulation. Flux and flux motor for motor design which you can integrate. This can be integrated. After acquisition we can do that. So these are the new features probably. After acquisition we have been integrated these things. So that is that. And then you have LD-SPICE integrations for SPICE simulations. And then integrating with FMI for third party integrations. This is an overall ecosystem of PCIM. And also to talk about depth about switches, you can use idle switches. You should know why you want to use idle switches. Whether to do a control design or frequency response, looking at body plot, acoustic to fine tune your PI gate and time constants, or you want to do system level simulations or component sizing, like sizing of an LNC values. In that case, you'll be using an idle switches like idle MOSFET, idle IGBTs, and so on. And you also have level 1, level 2, and thermal and SPICE. These are different fidelity. So, probably interested, I can just show you that in the live demo. Okay. So, keeping that in mind. So, as a power supply is another topic just said, right? So we can do a complete design with respect to ATAL solution. So flux peak for parasitic extraction and the PCM for doing analog digital circuit simulation, any kind of topologies with respect to converters, inverters we can do, design modeling and simulations can be performed. And then for thermal simulations, board level or component level, you can use electroflow simplan is there. And for PCB design, we don't want to do analog, we don't want to do digital domain and we want to do analog domain. In that case, we have tools like Polex for design for manufacturing and assembly, and also doing SI, PI, power integrity, signal integrity. These are the other flow which will be aware about this. Probably I would like to give more insight is that probably you apply a job for a all-running role. These are all the job description you will be getting it. It's not only you need to know the design aspect of it, you should know about the embedded system, control system, coding background, and you want to know about the PCB side as well. So there are a lot of process that you will go through. So better you want to go get into this key industry, whether it's a motor drive or power electronics, make sure that you guys are smart, but still I'm trying to tell you the experience is that If you get into a job description, what is the industry demands and needs from the younger generation in terms of people like you all. So you need to understand and get trained with those aspects. That's how you learn and then do. So that side, you can use our technologies as well, the tools. Any tools, maybe AICTE tools or third-party tools, but you need a platform to work on it. So that way you can do it. So this is another workflow which I would like to show you the live demo also, provided if I have time in the lab after this session. I can just show you the from a virtual to the real-time implementation. So this slide is very interesting slide. Is about it goes from motor design. So for example, I will tell you a requirement to do a project. Say you design a 3 kilowatt BMSM model. So if I say there is no available in the market and you want to design it from scratch, so you need some platform or tool to design it. So we have Flux Motor to design the model. What I would have a subject like electrical machine design, right? You calculate the length of the diameter, all those things you do, right? Winding, lab winding, wave winding. So these are all the analytical approach, spark equation method. But you need some tool to do the complex model, keeping time constraint in mind. You need some platform like this. These are the tools which you can design it. So Flux Motor and Flux is the electromagnetic simulation tool for doing electrical, mechanical, and magnetic simulations on the finite element base. You can design a model and then also do the structural, the multiphysics optimization, optimizing your magnets. So what are the factors for challenge of any motor design engineer is like efficiency. You should have a higher efficiency with a better cost, size, all these factors. But keeping this in mind, you should have not technically plus also commercial in terms of cost wise, you need to design it. So these are the challenges for any design engineers. With the help of a tool, you will be performing it. So that can be achievable is what I am trying to say here. Once you design the motors, bring that motor to a piece in, design the controllers, like doing feedback, like speed feedback or other for any EV applications, you want to control speed and torque. So in that case, advanced control techniques like sensor or sensorless algorithms can be simulated. And then you go to embed for code generation and real-time implementation. So from a virtual design to the real-time implementation on the HL, we have a complete workflow. You can do it. Okay. I have a few more slides probably. This is ACTIVATE, which is a multidisciplinary system simulation platform. Now ACTIVATE is called Twin Builder because I also talk about technologies like digital twin. It's another buzzword and buzz topic where everyone are moving, industry is moving towards that. So ACTIVATE is renamed as Twin Activate now. So the latest version is 2023 and it is a platform for you to do scripting. You can do block level, physics-based modeling, specific to electrical, mechanical, thermal, hydraulics, pneumatics, multi-body, any specific domains you want to model and do the entire system level approach of simulating it, you can do it, plus also doing 3D integrations as well. So when I talk about unique differences 3D, whether you want to do molecular dynamics or you want to talk about electromagnetics or computational fluid dynamics, you can couple the ACTIVATE with these tools. And also FMI, connectivity to digital mediator to send the data to a cloud platform. Whether it's the UDP protocol, MQTT, Kafka, these are the interfaces which to push the data. We have those connectivity part as well. Okay. So this is a overview of what ACTIVATE is. I'm trying to show you the overview. And pretty much if you have a legacy models from MATLAB Simulink, you can bring those models into ACTIVATE environment as well. If you have a Simulink model, you can bring in your .mat file as well as MDL or XLS file into our platform and you can simulate it. So this is a video where you can look into it. Okay. So I just want to show an app model with respect to the today's topic and the session which you have been listening many various speakers. Right? So this one such I want to talk about is this is what I said, how you can virtually model the entire vehicle, whether it's a two-wheeler, three-wheeler or a car, it has different systems. So one is the driving cycle. Driving cycle is nothing but I will have a driving pattern, you will be having a driving pattern. So we have a standard data which comes from a testing agency like ARI is a testing agency or WLTP standards from Europe or any standard agency who gives you the data. Based on those data, the driver is us, how you drive it. Electric motor, you know the torque and power demand. From there you have driveline, and then we also have the vehicle dynamics. That is represented as a mathematical model. And then you also have the inverter, battery packs. So battery packs, what level of voltage you are working on? 24 volts, 48 volts, 72 volts. What is the voltage range you are working on? You need to know whether the battery packs need to be connected. So one battery cell is 3.3 volt to 4.2 volts. So how many cells you need to connect in series to meet your power output in terms of density and power output? So that's why you design a battery packs. You may have seen someone who are driving EV vehicles, you put a charger, right? So how fast you need to charge. discharging aspects, range aspects. Those things you can virtually validate here. Based upon different driving pattern, how I'm going to increase my range. If I fully charge my battery 100%, how many kilometers I can go? What is the health of the battery? Whether it's equally charging, imbalance in charging, whether it's current protection, voltage protection, temperature side. Those aspects you can virtually see. Here is the model, just your mathematical model, where you can completely diagnose your actual speed was a desired speed, what is my vehicle range, what is my battery state of charge, and then instantaneous motor efficiency, what is the efficiency of the motor. And then you can look at the different points with respect to speed torque characteristics based upon the driving cycle. So this is the thing. So this model, another company called EEE Mobility in Pune. So this is also a vehicle engineers, they started a firm. They have lots of buses in Pune that are using it. Actually, this was one use case we actually built it, but we started giving it to the EV startup companies, and then they developed this model for a complete bus, the electric bus which is driving in Pune. So you can just see also there is a use case and like case study given. It's called EEE Mobility, company name. It's a lot of buses in Pune, electric bus orders have come and they'll be using it. That is one. Next time I'm going to show you the switch mobility. You have seen in Bangalore a lot of switch buses, switch mobility, right? EV buses. Those that is used by ATAL. So you're going to see that now. So one is Porsche. I have lots and lots of OEMs, global OEMs using ATAL for kind of EV modeling. Typically in terms of the console design, detailed design, system integrations. So if we do search it for a given time, it will be tough to digest all these aspects. But this is what how the industry is working on and how people are moving towards this aspect is what I'm trying to tell you. And then whatever best out of my little time you can take it or we can discuss offline as well. So this is one use case. And then as you have seen this bus switch mobility linked with Ashok Leyland. So they are using R2. So you can just look at for the range calculations, you can just look at your switch mobility. So I have a voice as well, but probably given time, it's publicly available on our website as well. Accurately predicting the vehicle range, opportunity for comprehensive modeling, understanding the most effective parameters, reducing the time and cost, accuracy, wide range of tools and expertise that we use our tools. So this is used in Europe as well as in Bangalore or seeing. I don't know whether you will have noticed that lots of switch mobility buses are there. Probably you can just see them. So they are using our tools, activities being used there, and other tools also within our portfolio. So you can check this case study in our ATAL.com. ATAL.com, go to case studies, you will find this testimonial. Okay, so I'm on time, my sister. So another couple of slides and then I will show them. How much time? 3:30 it is. Another 15 minutes? 15 minutes. So I'm on track. So ATAL embed, well, sir has given a lot of insight, more than me in terms of going into the depth what sir thought. It's so much, but sir went very more detailed in terms of explaining all the different parameters like what is the impact of ADC, PWM, and he talked about encoder, PCAP and all those models. But let me give an introduction about ATAL embed. This is also quite popular tool, which was earlier known as VISIM, and ATAL has acquired this product line and it is known as ATAL embed. Okay, and it is there from 2015 we named the brand, and which can go from a concept design to end product. So a lot of companies also needs module-based design in this. That is also another important aspect, like methods group in an organization like OEMs they need. So module-based as a process, as a V cycle or an inverted V, which goes from a concept design to the end product, which has different stages like model and loop. When I say a model and loop means we will represent the motor as a virtual model, as a path equation model, mathematical model, maybe as a state space equation or maybe a transfer functions. We can represent the motor, controller with the feedback sensors, and then the on-off switch. So everything virtual, that is MIM, called model and loop. Software and loop, you will have a DLL block as a code. The controller firmware will be running as a DLL block, dynamic link layer. But the plant will be a virtual model. See, virtual. When it comes to PIL, the real plant model, virtual plant model will be virtual, but the controller will be running real on the microcontroller target. That is PIL. And then HIL is nothing but real motor, the real inverter converters. I'm going to show that. I bought the motors, small motors, to show you the closed loop FOC algorithms. You can, I'll show that how HIL works. So this is a process goes from concept to end design. So probably you will be coming up on these terminologies and technologies when you really there is a demand and need for it, then you will definitely look for these topics. Otherwise, it will be like as a process you listen and then think. But if you really have an impact in your career going forward, you will understand more and you will be spending time on this. Okay? This is about model-based design in general. So this how the process involves with respect to design, modeling, and code generation. So when it comes to the design side, you do design modeling on the laptop. So tool is installed on your PC. You try to design your models, the complete model, and you try to